Okay, here are notes 6.5. One objective today, just be able to find the composition of two functions. Um, so basically, we're going to take two function and we're going to compose them of each other. This is conceptually basically a function within a function. So let's kind of take a look at what this looks like. So big X, so you don't necessarily have to write this. So if you think back of what it means to have f of 2, basically what this means is anywhere, this used to be f of x, but now it's f of 2, which means anywhere you're seeing x, you're going to put a 2. So a 2 would go here, here, and here. And then you would basically simplify from there and evaluate. So your input is right here inside the parentheses. Those are usually your x values, which are inputs. So you're going to take your input and then input it inside of the function. Now, what we're doing today is that normally in the past we've input numbers or real numbers. So we take a real number, we put it in here, here, and here, and then evaluate. The only thing different today is that instead of taking a number and putting it as our input, we're actually going to have a function as our input. So if f of 2 means that you're plugging a 2 everywhere you see an x, what about if I asked you f of 2x minus 1? So we would take this function, same thing we did before, anywhere we see an x, which is 3 spots, anywhere we see an x, we're going to put this 2x minus 1. So this entire thing, 2x minus 1, would go, so let's put blank spots, f of blank equals 3 blank squared minus 6 blank minus 10. And inside of each one of those blank spots goes our 2x minus 1, since this used to be f of x. That's what it started off as, but x is being replaced by 2x minus 1. So 2x minus 1, 2x minus 1, 2x minus 1. And then from there, you're going to be simplifying. That's the basics for today, is that we're just going to be learning about notations and how to do this. Because if you think about this, 2x minus 1 is an expression, and that's basically what a function is. A function is f of x equals some type of expression that meets a function or function rules. But yeah, so this is the gist of what we're doing. So let's go ahead and try out some examples. Actually, before we do examples, you need notations. So when you do a composition, there's different ways you might see the direction, say, do compositions. First one is this. This is basic standard way. If I had two functions, g of x and h of x, if I wanted a composition of this, this would say g of h of x. So this is one way. So if you notice, your h of x function is inside of your g function. Your h function is inside of the g function. Another way is like this. You'll see a small circle. This is not an O. It's a very small open point kind of thing, open circle. Be careful not to close it. If it's closed, that means g times h, which goes back to operations that we did last section. Another way you might see it is like this. G of h of x is another way you might see this. These are the three main ways that I've seen them in different books. There might be other ways, but these are the ones that I've seen in the past. So the ones I'll be using. Okay, first example, we got two functions. First, we have f of x is equal to this expression, 3x minus 1. H of x equals negative 4x plus 5. So this says f of h of x. Now, it's very important you read from the inside. So inside of your f function is an h of x function. So basically, we're going to take this function, which is your h of x, and put it inside of your f of x function. So there's your h of x, there's your f, okay? A couple ways you can approach this. One way is just start substituting right away. You know what h of x is. H of x is negative 4x plus 5. So we can rewrite this as f of, now instead of writing h of x, we're going to put negative 4x plus 5. Right? Now that's going to be like the screen that I just did a couple slides back, where now we have the f function, which is this one, and then instead of x, we're putting in 4x plus 5. So we're going to take this f function, which is 3x minus 1. So I'm going to rewrite that as, so my f function is 3, but instead of putting x, I'm going to put a blank spot, minus a 1. Now, inside of that blank spot is going this stuff, the negative 4x plus 5. And that's actually your composition. It just needs to be simplified now, but that's actually your composition. So to simplify this, you're just going to do some order of operations. So go ahead and distribute the 3. So 3 times negative 4 is a negative 12x. 3 times 5 is a positive 15. Minus a 1, and that That's the bell. Okay, negative 12x, 15 minus 1 is a 14. And that's how you find the composition of functions. I am okay if you want to go directly from here to this step right here without writing that f of negative 4x plus 5, if you can figure that out. I'll do that on the next one, actually, to show you what that would look like. So the next one wants h of f of x. So first off, work from the inside. I know I'm replacing, I'm putting f of x inside of h. So since it's going inside of h, let's go ahead and write our h function out and then put a blank spot. So it's going to be negative 4x. The x is going to be a blank spot plus a 5. Now this is saying that your f of x is going on the inside of your h. So that's my h, so the f of x should be going in there. So that's going to be a 3x minus 1 is your f of x. So 3x minus 1. All right. So now that you've plugged it in, you just simplify, and that's going to be about it. So notice that on this one, I did not write this middle step, which you can do if it helps you kind of figure out where it's supposed to go, but you don't have to. You can just write this outside function with a blank spot and just know this other function goes inside of there. So let's go ahead and finish simplifying this. So you're going to distribute the negative 4. That's going to be a negative 12x minus 4 plus 5, which is equal to negative 12x plus 1. Now, yesterday we went over the domains of functions when you add, subtract, multiply, and divide them. Today's composition, if you notice, I did not ask you for a domain. Main reason being is because we're going to be going over that either not tomorrow because we have a quiz tomorrow, but we're going to be going over that because it gets a little bit more tricky with compositions than other operations, how to find domains, especially with this type like these. So we're not really worried about domains yet, but we will be in a little bit. Okay, so just like before, we'll just go through the rest of these examples to help you out with your homework. So f of g of x. So first write the f of x function and then write the g of x function inside of the f of x function. That's why the f is on the outside, the g is on the inside. So my f of x function is a 3x to the negative 1. So I'm going to put a blank spot on this x part. Okay, take those off. So 3 blank negative 1, because that's my f function. Now my g function goes inside of there. I can see that because my g function is inside of there. So my g function is this 2x minus 1. All right. Now, normally when you're writing these out, you don't want negative exponents. So if you look at that group, the grouping of 2x minus 1, you can see that that entire group right here is to the negative 1 power. So you can use your negative exponent property and bring that to the bottom of a fraction. So the 3 actually has a positive exponent, so that stays where it's at. The 2x minus 1 is the one that comes down. All right. And some of you guys might be able to spot what the domain restriction is, but it's actually more than what you're probably thinking right now. You're probably thinking x is all real numbers except for 1/2, but you would be only partially right because actually x cannot be 0 either. And I'll show you the reason why in a little bit. Okay, so let's see here. So let's do f of x. So f of x is this, and another f of x. So you can compose a function within itself. So f of x means f of x is on the outside, so it's going to be 3 blank spot negative 1. And you have another f of x on the inside. So f of x on the inside is another 3x to the negative 1. Now there's different ways to evaluate this. Since we did a lot of power properties of power properties, let's go ahead and use some power properties here. So this is a power of products. So this negative 1 is going to go into there and to there. So it's going to be 3 times 3 to the negative 1 x to the negative 1. Now you can use other properties if you want, but if you notice here, this will be 3. You can use a negative exponent property, or what you can do is say 1 minus 1. Oh, wait, that's wrong. Negative 1 times negative 1 is a positive 1. Sorry about that. Let me erase that part. Positive 1. All right, so I'm going to go ahead and use the negative exponent property. So 3 to the first stays up top, x to the first stays up top, 3 to the negative 1 comes to the bottom, 3 divided by 3 is a 1, answer is x. All right, and you might think this is domain all real numbers, but it's actually not, and we'll go over why not tomorrow. And different notations here. G of hx is the same thing that it's been asking. So this is actually the same thing as asking g of h of x. It's just a different format. So if you want to rewrite it in that format, you can. If not, if you understand what it says, you can do that too. So this thing is h of g of x. They mean the exact same thing. Right, now you just do the same thing that you've been doing. So g of h of x means that you're going to write your g function, which is 3x squared, so blank, squared, plus 4x, so 4 blank. That's my g function with blank spots put in. Now I'm going to, within those blank spots, I'm going to put h of x, which is an x minus 2. All right, now it's just a matter of doing some order of operations here. Make sure on this part that you end up squaring first, so square x minus 2, which means x minus 2 times another x minus 2. You cannot distribute the squared to here because you have a binomial. This is not power of products. This is not a product, that's a difference. So there's no such thing as power of difference. So x minus 2 times x minus 2 is 3 times x squared minus 4x plus 4 plus 4, I'm not going to do this part yet, just minus 2. Okay, so all I did is I squared that binomial. Now let's go ahead and distribute the 3 and the 4. So it's going to be a 3x squared minus 12x plus 12 plus 4x minus 8. Now it's just a matter of combining like terms. 3x squared, so I'm going to cross them off as I'm combining them. 12x negative, 4x positives, and negative 8x. So those ones are accounted for, plus 4. Okay. There you go. That is your composition of g of h. Okay, composition of h of g. So this one. So one thing I want you to notice here is that all I did is I switched my h with my g. So instead of taking h inside of g, I'm now taking g inside of h. Some people might think this is the same thing, where we do the same thing twice. These should be the same, because when you multiply 5 times 6, same thing as 6 times 5. But keep in mind, this is not multiplying. This is a function inside of a function, which is fundamentally different than multiplying. So let's go ahead and see if we actually get the same thing or not. Now, sometimes you will. There are certain things that can be the same, but this is not one of them. Most of the, well, not most of the time, but because they're both infinite amount of examples, but more often than not, you will be seeing it that they won't be the same. So my h function is a blank spot minus a 2, because that's my h function. My g function is 3x squared plus 4x. Okay, so within our group, there are no powers on the outside, so I don't got to square it or anything. There's a number in the front, which is just a 1, so I got to get this out of parentheses before I can try to combine it with this minus 2. So to get it out of the parentheses, basically I just drop the parentheses, because you're going to multiply by 1. So this will be a 3x squared plus a 4x minus a 2, no like terms, so I box it. And you will notice that this and this are not the same. So basically, it's not going to get you the same answer if you just switch them around. Okay, so it does matter what order you put one inside of the other one. Example 4. More of the same thing. G, let's see if there's anything really special about these. 7 times 5, f of g. Nope. So just do the same thing we were doing before. Put one inside of the other. I think this was going to be like a pair share to help you practice with it. I'm going to skip over it and go right to this one. This is where it's kind of applied in real life. A clothing store advertises that it's having a 25% off sale. I'm sure all of you guys have seen some sales that have gone on. For one day only, the store advertises an additional 10% after taking, basically it's 10% after taking the 25% off. So You go in the store, you buy something, and it's 25% off. And then they say, okay, now that we applied the 25%, now we're going to apply the 10%. So you're going to use a composition of functions to find the total percent discount. All right, so this is asking us to basically build on what we've just been doing. So let me leave some space here. All right, so use a composition of functions to find a total percent discount. Now, this gets a little bit tricky. Basically, we should make two functions first off. So let's make an f of x function and a g of x function. Now, what does it mean to have 25% off? What that means is the total amount that you will be paying is going to be 75% of the original price. So what we're going to do first, actually even before I wrote these, is define my variable x. That way I know what you're talking about when you're saying x. So we'll say, just to represent what it means to have a discount, x will be the original amount paid, or amount, yeah, original amount. So if you take 25% off of an original amount, you're basically left with 75% of the original amount. So to find how much you're paying for f of x to account for the 25% off, it's going to be 0.75x. That will tell you how much 25% is off. It's not telling you how much you're taking off, it's telling you how much that you're paying. So you take the original amount, multiply it by 0.75, and that's how much you're actually going to be paying out the door for whatever you're buying. Okay, g of x is, we'll count this into be our 10%. So 10%, if you're taking 10% off, that leaves 90%, which is 0.90x. All right, so now it's saying use composition of functions to find the total percent discount. So the question becomes, is it f of g of x or g of f of x? Now, you got to kind of take into account what's happening first, what's happening second. So first, you're taking 25% off, which is this one. So that's the first thing that's happening. And then you're going to be taking that 90, the 90% off. So we're going to go ahead and put, since this is the first thing happening, we're going to say f of x. Okay, so that's the first thing that happens because the inside happens first. And then after we do that, we're going to take the 10% off, which is the 0.90. So we're going to take the f of x and then apply g of x to it. Oops, put that g kind of far. Okay, so that's what's happening. This is saying that you're taking that x value, the original amount, which is our x, then you're applying your f function. So first you're taking 25% off, so you're taking 75% of the original amount. And then from that amount, whatever that is, you're taking 90% of that amount also. Okay, and we actually have to simplify this because it says use composition to find the percent total discount. Let's go ahead and figure out what this looks like. So g of x is 0.90, and then the x part is your f of x, which is 0.75x. Okay. Let me go get a calculator. Hold on. All right. So let me move this stuff over. So basically, you're going to take 0.9 and multiply it by 0.75 and get 0.675. So that will be actually how much you're paying for the sweater after a 25% discount and a 10% discount. You're actually paying 0.675. Now, as percentage-wise, that's 67.5%. Now, be careful here. That does not mean that you got 67.5% off. That means that you paid, of the original amount, you only paid 67.5% of the original amount. So, but this wants us to find the total percent discount. So think about 100%. So you have 100%, 100, and then you're only paying 67.5% of that. 67.5, which is 32.5%. So if you take 100%, subtract 67.5, you get 32.5%. That's your discount. So 32.5% discount. Now that's a little different than what some people do with percentages. A lot of times people think, oh, I got 25% off, and then I got another 10%. So 25% plus 10% is 35% off, when in actuality you only get 32.5%. Now it asks us, what would be the sell price of a $40 sweater? So we know G of f of x is $40 sweater. So basically what it's asking is, sweater costs $40. So we're taking G of f of x, but instead of putting x, we're actually putting a 40 in there. Now we already know what this function becomes. It's going to be 0.675 x. So to find this, you're basically going to put 0.675 times 40, which is 40 times 0.675, 27. So this is equal to 27. So what will be the sale price of a $40 sweater? The sale price will be $27. Okay, and that's how you do that. So you got to figure it out like that. So tomorrow, bring me questions about any of the examples that we just did. Make sure that you specify which example that you needed help with, so that you know how to do the quiz. I do expect to see all of these finished. So tomorrow, the worksheet I gave you is not due until Friday, but you should be doing all these notes because it's open notes quiz tomorrow. Okay? Any questions you have, ask me tomorrow. All right. Bye-bye.